My name is Terry Cakebread. This presentation is about the benefits of elastic and nonlinear finite element buckling analysis compared to a codified approach. It was presented at the NASCC and World Steel Bridge Conference in Dallas in April 2012. The presentation will set the scene by talking about buckling phenomenon and about finite elements briefly, then focusing on the benefits offered by finite element buckling analysis and describing both elastic eigen buckling and nonlinear buckling analysis with a live software demonstration by my colleague Steve Rhodes. So firstly, about buckling. You won't need reminding about the I-35W bridge collapse, but it's worth remembering that the collapse was not related to the structurally deficient condition rating that the bridge had, and not due to corrosion, nor was it due to fatigue. The actual cause was joint failure at these locations, and essentially what happened was a buckling failure. We can see in the inspection photographs of the joint 5 years earlier that the gusset plates have got a significant bow in them. The nature of buckling is that compressive force applied to a member which is not straight, or in this case not flat, can cause a sudden loss of stiffness. There's little or no warning, and clearly it can cause catastrophic failure. Buckling is caused by the amplification of initial imperfections and of deflections due to lateral loads. It affects slender compressive members, whether they be made of steel or concrete, etc. To help us understand buckling in general, we can use this illustration from the AASHTO 5th edition. In AASHTO, or any other design code, the intention is that the design curve is conservatively below the real failure curve, according to some reliability index, and we recall that the real failure curve is in turn below the Euler buckling curve, showing us the load which would cause instability in a theoretical member with no imperfections, no yielding, and so on, and below the force which would cause yielding in stocky members. The design curve in AASHTO is helpfully labelled with compact, non-compact and slender divisions to remind us about the elastic buckling, yielding and the range in which the two interact. Finite element analysis can help us to identify the real failure curve. So what is finite element? Finite element method is a technique for analysing structures. By structure, here we mean pretty much anything which is not a fluid. So in this example from the UK, this lifting bridge has been analysed using finite elements, and also the hinge of the bridge has been analysed using finite elements as well. And whatever is being analysed, the principle is essentially the same. It is by notionally cutting up the continuum into small elements connected at nodes which can be handled mathematically. The basic principle of subdividing a structure into simple elements can be applied to structures of all forms and complexity. There is no logical limit to the type of structure that can be analysed. Consequently, finite elements provide the most versatile method of analysing structures available at present, and for many structures, the only practical method. Finite element analysis has been around since the 50s and 60s, and indeed our LUSAS software has been around for nearly 40 years. Widely accepted in the industry, AASHTO states any method of analysis that satisfies the requirements of equilibrium and compatibility and utilises stress-strain relationships for the proposed materials may be used, including the finite element method. But it's this flexibility to analyse pretty much anything brings us to our first benefit of using finite element buckling analysis over a codified approach. Sometimes we have a structure or member which is, for whatever reason, outside the scope of the code. Other times, finite element buckling analysis may be required by the code itself, or may offer more economical solutions. Let's take these points one by one. Typical cases where structures lie outside the scope of the code might be in the rating of existing structures. These may have features such as connections which are not covered by current rules. Girders may have thin plates which do not meet the shape limitations in the current code. In such cases, it could be potentially dangerous to try and use the code rules, as they were not intended for such structures. Indeed, there are many structures where, for some other reason, perhaps associated with fabrication, shape limitations cannot be adhered to, and thin flange or web plates are used. In such cases, local buckling can occur, and there are no rules in AASHTO 5th to cover such buckling failures, as they are excluded by meeting the shape rules in clause 6.10.2.2. A through girder bridge such as this may have connections falling outside the scope of the code, and may also have thin plates for the web or flanges falling outside the scope of the code for a second time. Even without those issues, the manual for bridge evaluation tells us that for such bridges we should consider the behaviour and resistance of compression members with elastic lateral restraints, and sends us to a reference outside the code. And that book gives us, in chapter 21, lots of detail about buckling analysis using the finite element method. And in fact, this kind of analysis has been undertaken many times for through girders, and this image is taken from a paper given at the International Bridge Management Conference of 2005, where engineers from Ramboll applied a range of methods including nonlinear analysis to save some bridges which have been identified as substandard. As well as concluding that nonlinear analysis gave a significant increase in load carrying capacity, they write, a restraint associated with the in-plane shear stiffness of the bridge deck exists in all through girder bridges that can be used through nonlinear finite element analysis to significantly increase bridge ratings. This restraint, which does not rely on moment continuity with the deck and is currently not recognised by design and assessment codes of practice, has now been applied in the economical rating of 30 bridges. The second of our benefits of using finite elements is sometimes the code itself requires us to do so. Two instances spring to mind here. First, in the analysis of bridges curved in plan, and also instability during construction. AASHTO comes close to requiring finite element for curved girders. The manual for bridge evaluation goes a bit further, saying analysis of bridges curved in plan should be performed using refined methods. Several state DOTs are making this a requirement in curved or skewed structures. But it's during construction that stability and buckling is of great concern to the designer. As AASHTO tells us, constructability issues should include stability during critical stages of construction. The investigation of stability shall utilise the large deflection theory. And GAI consultants used LUSAS to produce a full three-dimensional model for Avenues Walk Bridge in Florida, with the ability to consider all the issues of construction, including stability with large deformation theory, using beam and shell elements, as you can see here. And the last of our three benefits, sometimes buckling analysis using finite element methods can offer a significantly more economical solution. The problem is that when it comes to buckling, codes of practice, can be they American, British, European or whatever, are generally rather conservative, having been written with the intention that the same rules can be applied to a wide range of structural arrangements. And furthermore, they're written with new design rather than rating in mind. So structure-specific analysis can be less conservative and more economical. In the case of existing structures, a less conservative but safe analysis can mean the difference between a multi-million-dollar retrofit or replacement or no construction work at all, so it can save big money. In the case of new structures, the buckling is often critical during erection. This infers that a more economical design probably has no adverse effect on the structure in service. It will be no less durable, no more at risk. US consultants such as Gannett Fleming have therefore been using shell models of gusset plates to determine their capacity and understand their likely modes of buckling failure. In this model you can see beam elements framing into the shells with a gap shown here for clarity. So long as the analysis is fully understood, there is no reason why it should not be safe, and the potential to identify greater capacity can be significant. In a paper presented at the UK Institution of Civil Engineers in November 2010, engineers concluded that for the girders studied, nonlinear analysis indicated a significantly higher capacity than that determined from codes of practice. Taking the outgoing British standard as a benchmark, an increase of 53% was achieved by using the newly implemented Eurocode, and the predicted capacity was almost doubled by the use of nonlinear analysis. Unfortunately, AASHTO was not included in the study, but it would be a fair guess to put the capacity somewhere close to the old British or European standards. The implication in terms of cost saving, especially in rating of existing structures, is clear. Slender concrete piers provide another example of where following the code can be very conservative. Using the maximum axial load with a codified slenderness moment to allow for buckling is a very conservative approach, because the slenderness moment from the code is based on the likely deflection of the pier at failure. This slenderness moment approach is nonetheless widely adopted in codes including AASHTO and the Eurocode. The principle is illustrated in this UK publication for guidance on the assessment of concrete bridges. With a constant axial force P, codified rules would predict failure at a lateral load F corresponding to the failure at the right side of the graph. For a real pier, however, the failure load is actually the maximum load denoted in the graph, and this could be significantly higher. The simple code rules aren't able to take proper account of the large deflection theory, the cracking and becoming more flexible, the non-linearities in the system, and essentially ignore the lump in the graph. The Concrete Bridge Development Group says, to determine the actual capacity of a slender pier subject to axial load and applied moment and or transverse force, it is possible to perform a nonlinear analysis of the pier. The nonlinear analysis must model both the geometric, large displacement nonlinearity, and the material nonlinearity of the reinforced concrete section. An example of the use of this method gave a peak load 70% greater than that given by a conventional rating. Because of this, the analysis saved many thousands of pounds in strengthening works and associated disruption cost. This provides another illustration of how analytical techniques, which are considered too expensive to use in design, can be highly economic in rating. However, the benefits don't have to be confined to rating work. In this new design for a viaduct in the UK, consultant Atkins used nonlinear analysis to reduce the reinforcement required in these slender piers by over 60%. Let's now talk about the analytical options: elastic or eigenvalue buckling and nonlinear buckling. Elastic eigenvalue buckling is based on elastic theory, just like Euler. No imperfections, no yielding, no load following, and so on. An eigenvalue analysis of a simple strut will give you essentially the same result as a hand calculation based on Euler formula in books, but of course using finite element analysis we can apply this to any structure under any load system with any support conditions, so it's much more flexible. From the analysis we identify the elastic critical force or moments, that's like a value on the red line, and we also identify a theoretical buckled shape. But it's an upper bound, an unsafe value, so what's the use? There are, of course, several uses. First, AASHTO tells us that if the deformations of the structure results in a significant change in force effects, the effects of deformation shall be considered in the equations of equilibrium. It doesn't tell us how we decide that the deformation does or does not result in a significant change in force effects. On the contrary, Eurocode does. This clause tells us that second order analysis is required where the effects of large deformation are greater than 10% on top of a first order analysis. To confirm that literally, you need to do the second order analysis anyway. But the clause goes on to tell us that second order effects can be assumed to be less than 10% if the elastic critical buckling factor is greater than 10. The elastic critical buckling factor is the same as the eigenvalue buckling factor. An eigenvalue analysis therefore tells us whether it is necessary to perform a nonlinear analysis. So the eigenvalue analysis gives us a first assessment of buckling susceptibility. It also helps to bound the solution. When we adopt a full nonlinear analysis to find a buckling value on the green curve, we know that the real buckling value should be lower than the eigenvalue results, but above the design code result. It helps us gain an understanding of the likely behaviour of the structure. Lastly, the eigenvalue analysis provides a deformed shape which can be used to define initial imperfections for a full nonlinear analysis, which with LUSAS can be predeformed by that deformation automatically. A nonlinear analysis can be made able to take account of a whole range of things which are overlooked in a linear analysis of any kind, namely, when the material is not in the elastic range, a nonlinear analysis is required, when there are large deformations, when there is boundary nonlinear, lift-off, contact, tension-only members, etc., when there is creep or some other time-dependent effects. The principle of nonlinear analysis using finite elements is that there is incremental application of load. The stiffness of the structure is not constant, as in the linear analysis, but modifies as the load is applied due to yielding, cracking, large deformations, lift-off and the like. So in a nonlinear analysis the stiffness is updated based on these things each time the load is incremented. Within each load increment, a linear prediction of the nonlinear response is initially made and subsequent iterative corrections are performed in order to restore equilibrium by the elimination of the residual or out of balance forces. AASHTO describes this well and points out the important implication. Large deflection analysis is inherently nonlinear and superposition cannot be used. Load should be applied in the order experienced by the structure, applied incrementally with consideration for the changes in stiffness after each increment. It also provides very helpful advice. In conducting nonlinear analysis, it is prudent to perform a linear analysis for a baseline to develop insight into behaviour that is not easily gained from more complex models. This leads us to an analysis strategy something like this. First, carry out a linear elastic analysis. If you can't make that work and verify it, there is no chance you will get a nonlinear buckling analysis correct. Second, run an eigenvalue buckling analysis. This bounds the problem and gives us a deformed shape which is of later use. We take time to ensure we understand the behaviour of the structure, partly from the eigenvalue analysis, and generally to consider if nonlinear material effects, slackening of attached cables, or lift-off, for example, might play a part in the real behaviour of the structure. We might then undertake an initial nonlinear analysis using geometrical large deformations only, before finally adding material yielding and other nonlinearities for a final solution. This process helps us gain confidence and understanding of the structural model. With any finite element analysis, you should always do a sensitivity analysis to check that the results that you get are accurate enough. I have found that 24-inch linear down to 6-inch linear are about as accurate as 24-inch quadratic elements. So if you have those quadratic elements available, they're obviously better ones to use. An example here of mesh sensitivity checks from a report on a buckling problem carried out by our consultancy team shows that as you increase the density, it actually reduces the load factor. So note that initial checks can be unconservative, i.e. they overestimate capacity. So also even with a sensible looking mesh at the start, we can get differences, in this case of nearly 20%. By this process, we're finally arriving, hopefully with some confidence, at the green real failure curve. And let's remind ourselves of the study which showed the nonlinear approach gave almost 100% more capacity than the British Codes of Practice. The value predicted may be significantly greater, but it will be below the eigenvalue prediction. And Ashto says, a properly formulated large deflection analysis is one that provides all the force effects necessary for the design. Further application of moment magnification factors is neither required nor appropriate. That's not to say that you should omit to have a factor of safety. Of course you should include load factors in the analysis, and you will need to make a suitable assessment of material strength factors and so on. But if you have done the nonlinear analysis, you do not need to apply additional magnification for moments based on code rules. And the final analysis can look something like this, incorporating geometric and material nonlinearity. In this animation, the black stars show where yielding is occurring. This kind of analysis, underpinned by a thorough understanding of finite element analysis in general, with preceding linear analysis and elastic buckling analysis, and the use of codes, can give us a good assessment of the real strength of a structure. We can use it appropriately, but with confidence, based on all that we have brought together in our and we can check our understanding of the structural model. My colleague Steve will now demonstrate how a model like this can be constructed and analysed for buckling. Please see the next presentation in the series.